Hello, my name is John Pruden, and today I will be introducing you to the idea of computational chemistry using a simple counting theorem known as Polya's method. Now, I don't expect you to leave today with a perfect understanding of the vast field of computational chemistry, but I hope instead to show how mathematics and chemistry can influence and improve one another. Now, in chemistry, we deal with elements that combine with one another to create compounds. These can be as simple as two hydrogens combining with one oxygen to make water, or as complicated as a lengthy, multi-step reaction to create an organic molecule. In any case, we want to be certain that our end product is what we want, meaning that it has both the elements and the structure that we desire. Now, we can represent these reactions in a number of ways. You may remember writing reactions like this in high school chemistry, showing the elements as letters but neglecting their three-dimensional structure. But as molecules get larger, the structure of a molecule becomes more important in defining its properties. Molecules with different structures may be more or less stable, for example. Now, this new representation of the same reaction given before provides some structure for each reactant, or individual starting component of the reaction. But now we're left with a question. What will the structure of the end product be? Could this reaction create multiple products with different structures? And if so, how many possibilities are there? It turns out, yes, molecules can have the same number and types of elements while being different in structure. This is so common, chemists created a name for them. Isomers. Iso meaning equal, mers meaning molecules. You can have many different kinds of isomers, but don't worry about memorizing them. Just know that any given isomer can have very different chemical and physical properties from one another. Now, there are isomers that vary in their basic carbon structure, like this one, and there are isomers with the same carbon structure but a different location for key elements, like this one. This second kind of isomer, a stereoisomer, varies across a central component of the molecule, like a double bond or a ring. This is the kind of isomer that we will look at today. Now, as a molecule gets larger, its structure becomes more variable and thus more important in defining the molecule's properties. Even a simple molecule like C5H10 can have dozens of isomers, and since different isomers of the same molecule may have different properties, chemists can either use these differences for our benefit or watch out for potentially dangerous interactions. So it's important to know about every isomer possible. The thalidomide tragedy, which anyone from a Grafton class will remember, is a perfect example. Thalidomide was a drug with one isomer that was considered a wonder drug for morning sickness and another isomer that caused birth defects in children. Because of the lack of testing related to the second isomer, it was blocked by the US FDA, but thousands of children in Europe still suffered from these birth defects. So, knowing that isomers are important, let's look at a common example. We might change a molecule to make it more stable or more reactive, and a common change we want for a molecule is called fluorination, or the addition of a fluorine element to a molecule. The reaction I showed before is an example, the fluorination of cyclopropane. If we want to know what products this reaction can create, we need to look at all the possibilities. Frequently, chemists would simply draw every possibility, but now this is where Polya's method comes in. First, we assign an arbitrary number to each reaction site. In this case, a fluorine can replace a hydrogen on any location of this molecule, so we assign numbers like this. We then asked ourselves, hypothetically, how could we move this molecule in such a way that the end result looks like it did before we moved it? It's important to note that we're not actually moving a molecule, but rather using this as a thought experiment. This is how chemists think about the idea of molecular symmetry, how similar the regions of a molecule are facing each other or around an axis. Well, first we could do nothing, and the end state of this molecule would be the same as when we started. Secondly, we could rotate this molecule by 120 degrees, shown by this simple depiction. If we were looking at our real molecule, hydrogen 1 would move to position 3, and then position 5, and then back to position 1, which we can write in this form, 1, 3, 5. We could also rotate this molecule 180 degrees, shown with this simple depiction with the triangular molecule flipping over. Now looking at the full molecule, hydrogen 1 would move to position 2, and then back to position 1, which we can write the same way as before, 1, 2. And these pseudo-movements are called symmetry operations, and they define the symmetry of the molecule. We end up representing these pseudo-movements in a fancy notation called cycle notation. For cyclopropane, using the known symmetry operations, we end up with this chart. On the left we have the operations, in the middle we have the cycles, and on the right we have the cycle notation. This represents how many positions one hydrogen can cycle through before returning to its original position, and we can see the ones we discussed highlighted. The fun thing about cycle notation is that now we can use this to find a polynomial that represents the number of positions each element can cycle through according to that symmetry operation. So if, for example, we were fluorinating the molecule, we would have two kinds of elements, hydrogen and fluorine, represented as A plus B, and we would substitute this for that X. We then replace x with a plus b for each different symmetry operation and sum the resulting polynomials, which gives us this final polynomial telling us what isomers are possible for any combination of hydrogen and fluorine. So if, for example, we had 5 hydrogens and 1 fluorine, there's only 1 molecule, but 4 hydrogens and 2 fluorines gives us 3 possibilities. Using that polynomial, we now know that there's 1 molecule that uses all hydrogens, 1 molecule if you have 1 fluorine, and there's also 3 isomers if you have 2 fluorines, and 3 isomers for 3 fluorines. And this is important because we may not have drawn every possible isomer on our first pass, but now we have a way to make sure we were right. As a research tool, Polya's method can be helpful in what's called combinatorial chemistry. Chemists will model thousands of molecules, frequently various isomers, reacting with other molecules that the chemist wants to target. Finding out the number of isomers of a molecule in advance may lead chemists to selecting a better molecule to create more isometric possibilities, leading to more diverse and efficient drug discovery. Polya is also very relevant as a teaching skill. Polya's method may be used to find the number of isomers of a molecule, and then students can be asked to draw these isomers or create them with molecular modeling software. By teaching students with a computational method, we can hopefully create a generation of digital native chemists that intuitively understand computational chemistry and may be more able to exploit this process. Here are my citations. That's my presentation. I'd like to thank Dr. Burt for mentoring me on this project, Dr. Buby for running this course and helping me pare down my presentation to fit time, and our many external speakers for providing advice. Now it's time for Future John to answer questions.